Hello, this is my presentation entitled Pulsar Kick Velocity induced by another neutrino chirality flip and lower bound for the neutrino magnetic moment. My name is Daryel Manreza. I am from the Faculty of Physics of the University of Havana, and this work is in collaboration with Alejandro Ayala from UNAM, Santiago Bernal from UNAM also, Saúl Hernandez and Luis Hernandez from Mexico too. So this paper is, the preprint is in archive. If you want, you can see it. So as you know, compact objects are the aftermath of stellar evolution. We will focus on the special case of quark stars. As you know, neutron stars has masses around 1.4 solar masses. Here you can see a graph of different compact objects of different neutron stars and the mass, the measured mass of them, and you can see the distribution is around 1.4 solar masses with a radius around 12 kilometers and densities greater than the nuclear density, 10 to the 14 grams per centimeter cube. And also a feature of compact objects are their magnetic fields, which the highest in measured magnetic fields in the universe, up to 10 to the 15 Gauss in the case of magnetars. We will focus on the special case of these so-called strange quark stars, which are a special case of compact objects mainly formed by quarks with the special feature of the presence of the S quark. So we will make a model of a compact object made of this kind of matter. And we will be interested in search for a model to describe this observational evidence, which is called neutron star kicks. These pulsar kicks are a peculiar translational velocity of observed in pulsars, and they are explained in two scenarios. One is a natal kick, which is done when the neutron star is formed, and the other one is a postnatal kick, which is a velocity that the pulsar acquires during its evolution. In this reference that I give you here, they made a study of the motion of 233 pulsars, obtaining velocities as high as 1,000 kilometers per second and a mean velocity of around 400 kilometers per second. So these velocities of pulsars needs to be understood, and we want to make a model to describe these velocities. There are several models. One of them is the hydrodynamical driving kick, which is a mechanism that explains the first scenario of a natal kick when the supernova explosion occurs due to hydrodynamical perturbations, and this lead to asymmetric ejection of matter, which imparts a velocity to the pulsar. Other mechanism is the electromagnetic rocket effect, which is based on the emission of electromagnetic radiation from an off-center rotating magnetic dipole that imparts also a kick to the neutron star. And the other mechanism is the neutrino magnetic field driving kick, which is the one that we will study here. This kick is due to the asymmetric neutrino emission induced by strong magnetic field. It's based on the fact that the beta decays that occurs in the core of the compact object or the quark star emits, of course, neutrinos, and due to the magnetic field, the polarization of the electron spin fixes a direction of this emission of neutrino along the magnetic field, and this emission of neutrino works as a propulsion mechanism for the neutron star. The velocity can be computed just by conservation of momentum. The momentum of the neutrinos equals the momentum of the star, and a simple calculation shows that with the amount of neutrinos emitted, you can the pulsar can reach this measured velocity. This is the emissivity, this is the radius of the neutron star, and this is the mass of the neutron star. So we can rewrite this equation in this way, so that we have just the dimensions of velocity. This is the mass of the neutron star, this is the mass of the sun, the radius of the star, and this is an integral over the temperature of the cooling when the neutrinos are released, and this is the electron polarization, which is just the amount of neutrons, of electrons with a spin in the direction of the field with respect to the opposite direction of the field. And this is the calorific capacity. And the particles are electrons, quarks, up, down, and strange. The electron polarization is given by this expression. Note here that we take into account the quantization of the Landau levels given by this quantum number, which is the sum from 1 to the infinite, and this is the full expression for the electron spin polarization. Note that we didn't have made any assumption here, so we start from first principles and we compute this quantity without any approximation of low level field or high or very high field. So this is the full expression for the electron spin polarization. So we made this sum numerically up to infinity, numerically, of course. And we compute also from the thermodynamic potential, we compute the specific heat with this expression, which is a full expression also. And in these expressions, the spectrum of the particles is given by this expression. This work was published 2 years ago in this reference that I give you here, where we made a careful study of these quantities. But now we want to take into account another effect that in this electron spin polarization, which is the production or the neutrino chirality flip. This means that right-handed neutrinos turn into left-handed neutrinos, and they can leave the star without interaction. And the rate of production of these right-handed neutrinos is given by this expression, which was computed by one of the collaborators in this reference. And we are interested in computing the total reaction rate, which is the integral over the whole available phase space. So we compute that, and with that we can compute the time required for this process to occur, the chirality flip of the neutrinos. And this time should be smaller than the time required for the neutrino to travel one main free path in order to the neutrino can escape the star. So with this, taking typical values of the core of quark star, we obtain a lower bound for the neutrino magnetic moment, which is this quantity And this is the Bohr magneton, and it's, with a similar analysis applied to the core collapse during the supernova explosion, we can obtain this bound for the neutrino magnetic moment. This is the bound obtained by this work, this reference. So we have this interval for the neutrino magnetic moment. And this is the result for computing the velocity of computing the kick velocity, taking into account this this new feature that we're comparing now, that is the neutrino flip. And as you can see here, well, this is the kick velocity of the pulsar, and this is the radius. As you can, we computed for different values of the magnetic field, fixing a central density of the star. So as you can see, when we diminish the magnetic field intensity, the velocity decreases for the same value of a radius. And we, for the stronger magnetic field, which is around 10 to the 18 Gauss, we can reach 1,000 kilometers per second for the kick velocity. So as conclusions, we have shown that the neutrino chirality flip during the birth of strange quark matter neutron star is an efficient mechanism to allow the production of neutrinos to escape from the neutron star core, provided the neutrino magnetic moment is not smaller than 4.7 times 10 to the 15 times the Bohr magnet. The result of this work set a range for the neutrino magnetic moment given by this interval, and the obtained kick velocity for the neutron star conditions are consistent with the observed ones and span the correct range of radius for typical magnetic field intensities. Thank you so much, and see you.